Well, thanks for coming today, everyone. I'm excited to give this talk called The Rise and Fall of Dome, Insights into Continental Crust Formation in the Pilbara Craton from Isotopes in Detrital Minerals. And I'd like to extend my thanks to the survey for letting me share my work. It's a pleasure. So this talk is a combination of my PhD introductory milestone 1 background talk and my recent paper that's just been submitted in late 2022. So a bit about me. I'm from Llangollen in Wales, 24 people plus a few sheep. I did my undergrad in Scotland, where I was lucky enough to go to Greenland for a summer, and that's where I fell in love with old rocks, fieldwork, mineralogy, and my PhD really is a perfect intersect of them all. I spent a year waiting to arrive in Perth and a month of quarantine, and so far I can say it was worth it, and it was all made up for by brilliant fieldwork to the narrower terrain and Eastern Yilgarn with the survey. So what is the continental crust and why do we study it? Well, it's the rigid, most outermost layer of rock that extends down to the moho, and it really is this thin veneer akin to the skin of an apple that sits atop the mantle. The crust itself is highly varied in composition, being composed of a variety of lithologies. And despite comprising a tiny percentage of the bulk silica Earth, it is fundamental to life on Earth. And models of continental crust growth are essential. And why is that? Well, several ore deposits are linked to the formation of continental crust, for example, orogenic gold. Most life is found in the crust, most biomasses, around 80%, according to a recent study. The weathering of crust is intimately linked to the drawdown of carbon dioxide, and it's proven essential in regulating our climate and pulling us in and out of ice ages. And it creates this dynamic Earth we see today, where subduction recycles material in and out of the mantle. And the crust really is the essential geochemical reservoir. So the story of how Earth went from this ball of molten rock floating in space to the dynamic and differentiated world we see today is really yet to be fully resolved. And several different people have had several different ideas of how this might have happened. Back in the 80s, Armstrong modeled significant growth early on in Earth history, and then kind of consistent recycling of that early crustal volume since then. Whereas Goodwin in the 90s used present day age distributions of crust to infer that there was a sudden spike of crustal growth from about 1 billion years onwards. And more modern models are more holistic and use insights gained from a variety of different sources and isotopic systems. But regardless of that, some key questions still remain, and they include the timing of initial crust formation, how that early crust differed from the crust we see today, the nature of crust formation through time. Was it episodic? Was it driven by supercontinent formation, or was it a steady process ongoing? And another key question is, when did modern style subduction begin? Was it around 3J, or was it a intermittent process until it really got going later on in Earth's history? And so our models of crustal growth are really based on a quantitative understanding of several different processes. You might want to consider complete and partial melting, fractional crystallization and assimilation, a key igneous differentiation progress, and of course, metamorphism and sedimentation linked to those. So where does our quantitative understanding and modeling primarily come from? Well, it comes from zircon. Zircon probably forms our best record of continental crust growth. And crustal growth models are primarily based on detrital and magmatic zircon, and the uranium-lead, hafnium, lutetium, hafnium isotopes, and oxygen insights they contain. And peaks in zircon populations through time have been thought to represent periods of crustal growth, but it may be more difficult to interpret than that. They may be a function of preservation bias. Zircon truly is an ideal mineral, though, for understanding continental crust formation in that it incorporates trace amounts of uranium, so it can be used as a geochronometer. It's highly resilient and durable, and it can survive through multiple cycles of reworking and long-distance transport. So it really is a superb deep time archive, and is used to characterize a range of geological scenarios. You can even get histories from individual crystals, right through to understanding an entire orogenic system. Here we go. So insights from zircon, like I said, it is primarily used as a geochronometer, and oftentimes multiple events are recorded in a single grain. And zircon geochronology can be considered at the time when some major chemical change occurred, primary crystallization, regrowth, or metasomatism. Now, I know a lot of you are experts here, and this is all good stuff to go through because it forms a really nice background to the Pilbara case study that I'm going to present in a bit. It's also important to consider that crust formation is essentially a fractionation process occurring in the upper mantle. We want to know when the magma that formed that crust left the mantle, left this reservoir. So we target this age of melt extraction using model ages. And of course, they're named since they are based on a model of how a modeled reservoir evolved through time. And they can tell us when the melt that formed that crust was extracted from the mantle based on a number of assumptions, some compositional and some isotopic. That all sounds great, but there is a key question that remains regarding the use of zircon, and that is, to what degree are our zircon data sets biased towards particular lithologies, settings, and ages? Now, I mentioned that peaks in the zircon record may be a function of preservation bias of different tectonic settings, but another bias may come into play, and that is a compositional one. So here we have a simplified plot of weight percent silica against zirconium concentration in ppm. And you will see that with increasing silica, as the melt becomes more fractionated, the concentration of the zirconium increases. This results in zircon becoming more abundant in evolved felsic lithologies. It's not often you see well-formed zircon in a basalt, for example. So does this mean that we potentially have a biased record? Mafic crust generation may have actually dominated during times in Earth's history that are otherwise poorly represented by the zircon record. This is especially important since some estimates of crust growth suggest that up to 70% of present-day volumes were formed within the 3 to 3.5 GA interval, when mafic crust may have actually been the dominant means of crust formation. So we need robust models that account for the whole spectrum of geological compositions, and we really need to develop a tool that can help us know when mafic crust was being formed and also mafic crust was being extracted from the mantle. So does apatite come to our rescue? Well, apatite is a ubiquitous mineral found in a range of geological settings, from high-grade metamorphic rocks to carbonatites to mafic rocks. And again, from the same Pluton over in New South Wales, we can see the opposite trend as what was happening with zirconium. With increasing weight percent silica, the percentage of potassium oxide decreases. In other words, it doesn't want to be in a evolved felsic melt. It has a low solubility in silica-rich melts. This trend is also seen in laboratory settings where doped glasses have been modeled. And again, phosphorus is not happy in major silica rock forming phases. So what kind of insights can we get from apatite to help us build our models? Well, we can get an age using uranium lead, but perhaps with some complications. We can also get isotopic traces from the lutetium, hafnium, and samarium neodymium systems. We can also use the more diverse cargo contained within apatite compared to zircon of trace element geochemistry to discern source rock geochemistry. as was done here, where increasing strontium percentages within detrital apatite allowed the source rock to be broadly constrained in terms of its nature, in terms of how felsic it was. It's also important, though, to consider that in situ analyses of apatite, as has been done here, are really important because you need to consider the grain conditions. What do the isotopic ratios you obtain from apatite actually mean? And I think it all comes down to it's not as straightforward as zircon, uranium, lead geochronology. So how do we translate this all to our story? Well, we want time integrated measurements of isotopic traces, model ages, as well as a uranium lead age, potentially. This can be complemented by our trace element chemistry to discern different types of apatite populations, mafic ones from more intermediate or felsic apatite. And I envision us constructing a model for mafic crust formation through time, taking into account a variety of different isotopic systems and geological processes, as has been done here by Hawksworth in 2019. And of course, the ideal goal would be to integrate this with zircon, with well-established zircon data sets to gain a more holistic insight into crust formation through geological time. So this seems all straightforward. Why hasn't it been done before? Well, apatite is a powerful but quite problematic tool for unraveling crustal formation. And complication number one is common lead. So uranium lead data typically sit along a two-component mixing line in Concordia space between a time-significant radiogenic lead population and an initial common lead component. And common lead is non-radiogenic lead that has no significance in terms of dating a rock. And common lead introduces significant uncertainties, and it does complicate our age interpretations. So the presence of undetected and especially uncorrected common lead is very detrimental to uranium lead dating, and you must correct and account for it. In other words, you have to subtract common lead from the time significant radiogenic lead portion in your analysis. So how can we go about doing this? Well, we can fit a regression line. We can perform a best fit regression through the isotope ratios to get a uranium lead age. This can be relatively straightforward for magmatic samples where a single mixing line with a single common lead source is defined, but it can be especially difficult to constrain when you have detrital populations where there may be several different populations present. So, of course, you can use a model of how terrestrial common lead evolved through time, typically the Stacey's and Kramer's model from the 70s. So you can use your initial apparent age that you estimated from your uranium lead and an appropriate terrestrial lead evolution model, and you can then reiterate your age, taking into account the model until no subsequent change occurs. But then how do you know if the model that you're using is valid? Well, you need to do some model validation. And this model-based approach can be validated using the intergrain variability of common lead. So we're effectively calculating individual apatite isochrons here, where multiple ablations analyses have been performed on the same crystal. And you can even take this down a scale by doing individual subsets on the same ablation. So we're effectively checking the validity of using the Stacey's and Kramer's lead model to ensure that our correction is correct. There's also another complication here, and you have to distinguish between primary apatite, that is the crystallization age of apatite, or some other secondary process that's occurred. So apatite compared to zircon has a lower closure temperature. So the uranium lead closure temperature of apatite may record processes, lower temperature processes in the mid to upper crust. And natural apatite is modeled to likely close to outwards lead diffusion at approximately 375 to 600 degrees. But closure temperatures should be considered on a case-by-case basis. They're often influenced by grain size and the presence of fast diffusion pathways. So thermochronology is when a mineral cools through a closer temperature for an isotope system of interest. So apatite uranium lead ages may not actually be telling you when the grain crystallized, rather it might be telling you when some secondary other post-magmatic process occurred. So a potential solution to overcome this complication with apatite is to use the isochron dating technique. So at crystallization, all grains, or detrital apatite perhaps, in the system have the same samarium-neodymium ratio, just different concentrations. So at time 0, the isochron is defined by a horizontal line. And obviously through time, the greater the initial concentration of parent, the greater the concentration of radiogenic daughter product will be. So you form a sloped isochron. It's also important to consider that this approach will only work if they're cogenetic. In other words, if they're from the same magmatic system. And so we get the age from the interception on the y-axis. So now let's apply what we've learned into a case study, kind of pulling together all the things I've just spoke about. Why study the Pilbara Craton? Well, it consists of Paleoarchean to Paleoproterozoic continental crust, and few places in the world offer such extensive exposures of Archean crust, and therefore insights into ancient continental crust production. And remember how I was talking about between 3 and 3.5 GA, mafic crust formation may have actually dominated, and that was when most of the magmatism occurring in the Pilbara was taking place. And remember, I said up to 70% of present-day crustal volumes may have been generated through this time. So it really is a critical window that we need to better constrain. So sands were collected across the East Pilbara terrain over different lithologies. Tributaries of the Nullagine, the Grey, Ewell, and Okover River were sampled. And you may be wondering why sand samples? What can they tell us? Well, they can be a broad and efficient snapshot of the geology in the area. And these samples may also provide information on rocks that no longer are outcrop or no longer extensively outcrop. And detrital zircon studies have proven useful in unraveling the crustal evolution of different areas in the past. So it would be an exciting opportunity to integrate the apatite detrital story with the zircon. So we want to know, how does detrital apatite behave in Archean terrains? So here is the recipe from going from a bag of sand to a hopefully apatite-rich and zircon-rich mount. We sieve at 425 microns. We then take it to the JCR Whiffley table, which separates minerals out on density. We then put it through heavy liquid at 2.8 grams per cubic centimeter. We then remove the magnetic fraction using a Franz table. And finally, hopefully, we end up with these beautiful epoxy mounts with potentially hundreds of zircon grains on them and apatite grains. And all equipment I've used during the study is here at the John DeLater Center. I, of course, do in situ geochronology using the LA ICP-MS and the SHRIMP2. And then I can refine some of my images using my imaging and petrography using the TEMA and Clara and Mira scanning electron microscopes. So did I end up with good mounts full of apatite and zircon? Well, it wasn't that bad. Here we have our apatite mount, and this Y shape here is just for navigation. It's kind of a way up structure in a way. And here is our zircon mount from the same. So decent concentrations were yielded after the process. So what do our grains look like, and what kind of observations can we make initially? Here we have the top 2 rows contain some representative zircon from the Pilbara study. And the bottom row here contains apatite from the Pilbara sands. And you may notice that older grains here are smaller, lower aspect ratios, highly damaged, rounded. And this is potentially a function of consistent reworking within Pilbara basins, whereas our younger grains here are generally larger, more euhedral, and with more pronounced zonation, which is kind of curious since they must have travelled relatively far to arrive in the Pilbara, and we'll touch on that later. And apatite appears largely homogeneous. There's no pronounced zoning, and they all have kind of consistent grain sizes across the entire detrital population. So here we have a simplified geological map of the East Pilbara terrain, showing some of the main drainage basins and where I collected my sand samples from. And to the side are heavy mineral fractions that were obtained following processing, and adorning them are KDE estimates for concordant zircon ages. And so what kind of initial observations can we make here? Well, you'll notice that sand collected directly atop granitoid domes, so for example, sample 18 and 19 here, are relatively unimodal in age component. And this age component corresponds to the crystallization age of the underlying supersuite. Whereas those collected above greenstone, so for example, sample 17 or sample 27, they have more varied age components as opposed to the granitoid domes. And it's also important to note that ages obtained from underlying geology and overlying science need not be congruent. They can actually be significantly different. And another observation is that modern day drainage systems seem to have little impact on the ages I obtain. So samples downstream from each other generally do not correspond in terms of age components obtained. So how can we account for this age distribution? Well, we can think in terms of intrinsic zircon load versus imported or exotic zircon cargo. So for the granitoid domes being very felsic in nature, of course, they're going to have a large intrinsic zircon cargo. And of course, they will incorporate some non-Pilbara exotic zircon. When we move to the greenstones, they are going to have a lower intrinsic zircon load, being more mafic generally, and in composition. And with the same exotic zircon cargo, they're going to be far better records of non-Pilbara far-traveled zircon. They're not going to experience, the exotic zircon isn't going to experience as much dilution as the granitoid domes. And this highlights what I mentioned earlier, that the zircon record, if you were just to look at the granitoid domes, they are biased towards felsic lithologies. And the mafic greenstones are otherwise poorly represented by the detrital zircon archive of the East Pilbara terrain. So here we have a summary of the ages I obtained from the Pilbara sand dataset. And here we have stacked KDE estimates for ages obtained from detrital apatite in orange and detrital zircon in blue. And I just want to draw your attention to the break in the y-axis here. So the light orange age component here represents all 207, represents all apatite ages attained. There was no correction performed, no filter carried out. Whereas the bold orange here is filtered for apatite ages with an F207 less than 30%. The light blue cloud here is unfiltered 207, 206 zircon ages, whilst the solid blue is filtered for analyses within 10% of concordance. So what kind of observations can we make here? Well, apatite uranium lead ages seem to define a single age peak at approximately 2.9 GA. And you could say that this is consistent with apatite being labile, and its proximal first cycle detritus derived from the Pilbara craton. Whereas zircon, being more refractory and durable, seems to almost represent a very comprehensive archive of Western Australian geology since the Archean, with ages spanning from 3.6 GA to as young as 0.2, 200 MA. Yes, so apatite is more temporally restricted than zircon, with our 207 corrected ages implying a discrete population that closed to radiogenic lead diffusion at 2.9 GA. And you may notice this scattering about the lower intercept here, and it is greater than 1, the MSWD, and that probably implies differences in the closure temperature of different apatite grains as a result of the volume-controlled lead diffusion I was talking about. But on average, they close to radiogenic lead diffusion at around 2.9. But as I spoke about earlier, what is this age actually telling us here? Is this a cooling, a resetting, or a crystallization age of the apatite? We know how vulnerable the uranium-lead system is in apatite, so let's look at two more resilient isotopic systems with closure temperatures as high as 800 degrees and 700 degrees here. So using isochrons calculated from our detrital apatite population for samarium neodymium and lutetium hafnium, you will notice that these ages are kind of remarkably in agreement with each other. And there is a discrepancy between the age maxima obtained from apatite uranium lead and the isochron ages obtained from these two separate systems. So what's going on here? Why are there discrepancies in the ages we're obtaining? Well, samples 18 and 19, which yielded over 75% of apatite uranium lead analyses, were collected from sand above the Bishop Creek monzonite, which crystallized at approximately 3.2 GA. At around 2.9, the emplacement of the split rock supersuite, which was this voluminous intrusion of magma into the East Pilbara terrain, heated the apatite to a point above the uranium, to above the lead closure temperature of approximately 500 degrees, but not exceeding the closure temperature of these two systems. So we're seeing the whole scale thermal resetting of apatite uranium lead in the East Pilbara terrain at 2.9 GA. And our uranium lead age is a thermally reset age, so it's not a crystallization age of the apatite. And we can also assume that all our detrital apatite is from a single component. This is confirmed or very supported by the similar ages we've obtained from these two separate isotopic systems. We can also use the initial ratio of neodymium we obtained to kind of refine our provenance interpretations for detrital apatite. So the red overlaid square here is derived from the initial neodymium ratio obtained for the entire detrital apatite population. And these black spots are whole rock neodymium analyses collected from the crystalline basement lithologies of the Pilbara craton from the survey. I'd also like to draw your attention to the europium anomaly of the detrital apatite population, which was 0.73. That's a weakly negative signature consistent with an intermediate source. So the europium budget was not significantly depleted during plagioclase crystallization. There were prolonged periods of discontinuous mafic to ultramafic magmatism that formed the Mount Bilroth supersuite here. And such magmatism is of appropriate age and location to have at least contributed to the detrital apatite population, which then became reset during the emplacement of split rock supersuite later on during the later stages of the East Pilbara terrain. So, whilst the majority of apatite is seemingly derived from the granitoid lithologies of the Mount Edgar Dome and other similar granitoid domes, a more intermediate to mafic apatite population has seemingly contributed to the apatite that was reset during this event. And of course, we can also use zircon, epsilon hafnium to enhance our provenance interpretations. It does seem that apatite provenance seems relatively straightforward, given that we know it's proximal from the Pilbara. But for younger zircon grains, it can be complicated by source regions having overlapping ages. So these dashed areas represents 75 peak density confidence with a fixed KDE bandwidth of epsilon hafnium 1.5 and age 25. But in other words, these are where apatite from this area, zircon from these different orogenies may plot. So we can see that Proterozoic detrital zircons in the East Pilbara terrain are derived from multiple sources. And it's interesting that the Musgrave province here is the dominant supply of Mesoproterozoic grains, as opposed to the more evolved Albany-Fraser origin. It's also interesting that we are getting some very young Mesozoic grains with ages of between 2 to 300 MA and extremely positive epsilon hafnium signatures. These are likely derived from the Lhasa block. The Lhasa block was a east-west trending terrain that is now incorporated into the Himalayas, but during the Mesozoic was actually just offboard from the West Australian Craton. And recent work has showed that there was sufficient detritus flow between the two terrains to exchange material. So this detrital dataset is kind of providing further evidence for a proximal Lhasa terrain where flow occurred between the two blocks during this time. But how are these younger zircon getting to the Pilbara, and why are they so well preserved? So despite a period of stability and restricted sediment input following the breakup of Gondwana, we still have a large cargo of exotic non-Pilbara detrital zircon grains. The cover of the East Pilbara terrain consists of isolated Cenozoic successions of alluvial material, duricrust, and pisolite. And this fragmentary layer occurs throughout the West Australian Craton and represents the remnants of a once more extensive fluvial system that was originating from the Paleo South Pole during the time. This layer was later modified by Permian glacial activity, and we had the whole scale movement of material in a northwards manner during this time. So we believe that this stratum represents a reserve, almost, of well-preserved zircon, which is still being periodically eroded, releasing grains into contemporaneous river sands of the East Pilbara terrain. So the detrital zircon archive of crust formation, and here we have a epsilon hafnium plot for the Pilbara age zircons. So we can say that the detrital record of the East Pilbara terrain closely tracks and conforms to the crystalline record here in terms of ages. However, a notable record of detrital zircon sit beneath Chur and appear to represent more evolved lithologies not readily represented in the crystalline record. From around 3.5 GA, we're seeing evolved sub-Chur epsilon hafnium signatures being punctuated by vertical hafnium mixing arrays, which is consistent with patterns we see in the crystalline record here. Older lithologies were episodically refertilized with juvenile magma, resulting in these mixing arrays we see here. The interlude between such rejuvenization events is characterized by continued isotopic evolution in several stacked arrays, best characterized by a 176-177 lutetium hafnium ratio of around 0.010, which is consistent with Archean TTG formation. And these periods of mixing with more juvenile material are associated with significant crust generation and the emplacement of supersuites that would go on to form the granitoid domes of the Pilbara. So why are we recording a more evolved epsilon hafnium record in the detritus of the Pilbara? And why isn't it readily seen in the crystalline record? Well, the detrital zircon of the East Pilbara terrain are seemingly recording the unroofing of evolved crust. Here we have box and violin plots for the detrital epsilon hafnium signatures compared to crystalline values from the East Pilbara terrain. Blue is the detrital record for selected time intervals, whilst green is the crystalline record from the same time periods down here. So what's this figure telling us? Well, despite having similar median epsilon hafnium values between detrital and magmatic zircons, detrital zircons show a wider compositional range and encompass more evolved epsilon hafnium values through time during each interval. I will say critically, the interquartile range for the oldest 3.5 to 3.4 interval encompasses more evolved epsilon hafnium values than the crystalline record here. This model fundamentally relies on the zonation of domes, which has been very well displayed by recent work in the Mount Edgar Dome by Gardner. And the spatial zonation of epsilon hafnium values we see in the domes is a function of melts becoming more evolved through the Archean, reflecting the increased working of earlier crust rather than juvenile material. So the evolved zircon shed from now destroyed dome cores, you could say, dome cores that have now been subsequently destroyed or assimilated. The zircon was shed from these dome cores. You can imagine a target where you have evolved zircon here being shed and lost into the detrital record, and they have been preserved within basins during which extensive reworking eroded and transported the zircons to their present resting place. So, is the detrital record of the East Pilbara terrain a more extensive archive of the earlier, more evolved crust of the Pilbara, in contrast to what the crystalline record presently offers? So here we have a model to kind of pull it all together. We have a schematic block diagram of the East Pilbara terrain showing the present surface here and the hypothesized pre-erosion surface of domes. And of course, inputs into the denuded craton are shown. We see this zonation very clearly in the Mount Edgar Dome, where we have very evolved cores surrounded by juvenile rims of domes. The destruction of evolved dome cores is recorded by the detrital zircon record. So you can imagine that we have a dome, which is then lost into the detrital record. And taking into account both of these insights, we get a even better complete picture of crust formation and destruction in the East Pilbara terrain. So the detrital record is like an old book. Once you look past the damage, there is a good story of crustal evolution in the East Pilbara terrain. And thanks for listening. And I hope to see you all again in the field soon. And again, thanks to the survey for having me. Any questions?
Hi, yeah, thank you. Thanks, Anthony. And sorry about the stuff up at the beginning, which is entirely my fault. Fascinating talk and really, really nice data. So any questions?
Yeah, I've got a question. Can you hear me?
Yeah, I can hear you.
Yeah, just going back to that diagram you had early in the talk with the various models of crustal growth. Is there any one of those particular models that your data supports or is able to feed into to support?
Yeah, thank you for that question. This is it's been interesting in that we have noted that apatite. We were hoping it was going to complement the zircon record of the Pilbara, but it is so susceptible to this thermal resetting that we have gained some insights into mafic crust formation in the Pilbara, but it's not as extensive as we hoped. So we need to perhaps look at the crystalline record of apatite in the domes to see if that's experienced the same thing as the detrital record.
Yeah, okay.
Any other questions?
Still.
Actually, I've got a question. I've got a comment. Really nice talk. I think the one interesting thing is that I think the split rock supersuite, split rock clearly is very, very a big event and high temperature granites coming in at that time. But this really confined to the southern part of the East Pilbara terrain. So is that where you've sampled? So it would be interesting to see if you sampled away from that area, as to whether you would still get that 2.9 resetting.
I agree, actually. And another source of apatite, detrital apatite, was sample 26 here in the Shore granitic complex. And I think it's the Mulera granite has also reset the detrital apatite here, which is part of the split rock supersuite. So I agree with you, perhaps moving more northwards away from this supersuite could perhaps show some non-reset apatite.
It's actually intriguing that that there's a spatial restriction to the southern half. We see that in other data sets as well recently. The other thing I'd like to comment, which when your model is really nice with the doming, is that there's some studies from the American group around Basil Tikoff. I think Nick Roberts published a paper recently, and where they show that the dome evolution is mainly in solids, subsolidus conditions. So it's maybe melt assistant ductile flow, but it actually studies steady state most of the time. And during emplacement, the granites were probably sheets, so then formed into a dome later on. Most of the time, maybe not the split rock, but anyway. But if that's true, that actually would even amplify your model a bit more, support it more, because then most of the domed sheets in the core would be eroded. Is that right? I don't know.
That's right. Yeah, they're preferentially eroded, either forming areas of more buoyant melt or areas of preferential erosion during the unroofing of the domes.